All right, so this chapter deals with electric potential and potential energy and kind of finishes off with how those relate into capacitance. So first of all, we got to talk about what's called potential. So in V here stands for potential. You'll often hear it called voltage. Some professors every once in a while always like, don't ever use that term ever again. We don't say meterage, so don't say voltage. So potential is measured in volts. But some people think it's improper to call it voltage. I don't care. Voltage, technically the correct term is potential or electric potential. So the reason we call it electric potential is because it's actually related to potential energy. And you can see the expression for potential energy here of something that's charged. So is Q times the value of the potential. And so potential energy depends on potential as well as the charge of the object you have. So if you look, we had gravitational potential last semester. So what was the formula for gravitational potential energy? mgh or mgy, same diff. So in this case, this part of it might be analogous to potential. It's independent of the object. The object has to be experiencing gravity and be a certain height above the ground. But this is the thing the quality the object must actually have. To feel gravitational potential energy, you got to have mass. Well, in this case, our potential energy is QV, and so potential is kind of analogous to being a certain height in a gravitational field or something like that. But the property the object itself must have to feel this is charge rather than mass. So kind of think of an analogous to that. And if QV is your potential energy, then your change in potential energy is going to be Q times the change in potential. Just like if you want to change the potential energy here, it'd be mg delta H, typically is how we'd get it, change in height. Cool. Typically, if you get a change of potential energy, it means work has been done. And so that change of potential energy is also equal to work here. Finally, one last expression to compare here. This shows how your change of potential can be related to the electric field, and distance as well. So we'll see this come into play again once we do capacitors here as well. Cool, so let's kind of just jump right in and see some examples. One thing you should know about potential here is electric potential is not a vector. Is that a good thing or a bad thing?
It's not a good thing.
It's a great thing because it means when you go to add potentials due to different point charges or something like that, you don't have to add vectors. You don't have to worry about the Pythagorean theorem or anything of that sort. You just add them together. One thing you should know is potentials can be positive or negative depending on if Q is positive or negative. So here is where you're actually going to plug in the value of Q, whether it's positive or negative. Positive Q's lead to positive potential, negative Q's lead to negative potential. We'll kind of deal with that. So let's just say I had a stone here and I let go of it. Where's it going to go? Down. Why? Gravity. Tell me in terms of potential energy. Why is it going down?
Because there will be a charge pulling it down.
So lowers the potential energy. That's the key. So you could say gravity is the force responsible for pulling it down, but if you look at it in terms of potential energy, it's going to fall because that lowers its potential energy. Spontaneity always goes in the direction of lowering an object's potential energy. If you want to raise its potential energy, work is going to have to be done. Spontaneously, it would go the other way around. So in this case, I'm going to make this a positive charge and not a pebble or a stone. And I'm going to look at this as being like 50 volts, 40 volts, 30 volts, 20 volts, 10 volts, 0 volts. And so we're on a potential gradient here. So what does this positive charge? In fact, let's just put the positive charge in the middle here. What does this positive charge want to do? Why does it want to go down? Not about lowering the potential. I couldn't care less if we lower the potential. I care about lowering the potential energy. So what is the potential energy here at the halfway point for this charge? Well, what's the formula for potential energy? Q times V. So what's its potential energy at this half point here? Just positive Q times 25V. So I'm just going to call it 25Q. Okay. If it goes this way, what would its potential be at the bottom? Let's go to the extreme. 0. What would its potential be at the top? 50Q. Does it want to go down or go up? It spontaneously wants to go down. So positive charges, to lower their potential energy, go to lower potential. Well, that makes sense. And once again, we're defining everything for positive charges. But if I throw a negative charge in there, let's just call it negative Q, what's its potential energy at the halfway point? Cool. At the bottom?
0.
At the top?
Negative 15.
Cool. Where does it want to go? It wants to go to more negative potential energy. More negative means lower. And so in this case, it's weird because a positive charge goes to lower potential spontaneously to lower its potential energy. But a negative charge goes to higher potential to lower its potential energy. And so the direction is always about lowering your potential energy, but whether or not that's higher or lower potential depends on if you're a positive or negative charge. But if you just remember that everything is defined relative to a positive charge once again, positive charge goes to lower potential to lower its potential energy. The negative charge is the exact opposite.
Could you say that the floor or the ground is negatively charged? That's why the positive is attracted towards it?
So you could totally say that. So something's creating this potential gradient, and it could be that the bottom here is negatively charged or something along those lines, or at least there's negative charges here, or it could be because there's positive charges up here somewhere, or both, or, something's creating this gradient. Cool. So let's say I let go of this marker. Where's it going to go? Down. Well, let's pretend that I've got something here, and this new marker is something you've never seen before. I have made this out of antimass. It has exactly all the opposite properties of mass. What is it going to do when I let go of it? Go up. This is why this seems a little strange. For mass, we don't have antimass or antimatter that we're ever going to experience on any kind of normal basis during the day, and we just always expect it to fall, so to speak. But for charges, we have pluses and minuses. We have opposites. And so we have to define things relative to one and just know that the opposite charge does the exact opposite. And it seems weird relative to gravity because we're not used to seeing opposites, masses. Not something you're going to experience. All right, let's work out some examples here. So number one here says an electron, and it gives you the charge and mass of an electron, is accelerated from rest through a potential difference of 1 times 10 to the negative 6 volts. What is its final velocity? So what are we doing here? We're accelerating this electron from rest, and it ends up with a velocity. So relative to kind of what we talked about here, what's changing for this electron? Its speed is, that's true, but relative to what we've talked about, what's changing? Its potential energy. Is its potential energy going up or down? It's going down. How do you know? We could figure it out real quick, but how do you already know? What's happening to its kinetic energy?
It's increasing.
It's increasing. So if we can assume conservation of mechanical energy, we could say that the change in potential energy plus the change in kinetic energy adds up to what? If we assume conservation of mechanical energy, 0. So we usually say that the initial potential and kinetic equals the final potential kinetic, but this is another way of saying the same thing. So if we rearrange this a little bit, we could say that the change in kinetic energy equals the negative of the change in potential energy. Again, another way of expressing the conservation of mechanical energy. So in this case, if we have 1/2 mv squared final, what was the initial velocity? Since we accelerated this thing from rest. Good, so final minus 0, no initial kinetic energy whatsoever. So in this case, what's our change in potential energy actually equal to? Q delta V, right? So in this case, the negative of our change in potential energy, what's the Q value for an electron? It's given in the problem, by the way.
1.6 times 10 to the negative 19 coulombs.
Cool, and is it positive or negative for an electron?
Negative.
Good. And what is the change in potential, change in V, delta V? Good. And so in this case, we'll get V final squared equals, I think I even told you to round this to 1.6, or did I say 1.602? Yeah, I said 1.6. We'll round it then, make our lives easy. Multiply these, negative times a negative is positive, and you get 1.6 times 10 to the negative 25. Sure. And take the mass of an electron is given 9.11 times 10 to the negative 31 kilograms, and I guess times 2.
I have a question. The delta PE is negative, right? So PE final minus PE initial, could it really be negative? PE final less?
Right. So your change in PE is indeed negative. But once you factor that negative sign in, this entire side of the equation becomes positive. So notice if that negative sign weren't there, notice and it's there because when I move this to the other side, it becomes negative change in potential energy. So, but notice potential energy and kinetic energy aren't both going to go up. As potential energy goes down, kinetic energy goes up. One's positive, one's negative. Cool. So they're not equal. They're equal in magnitude, but opposite in sign. Okay. Cool. Can somebody get me a final velocity?
592.67.
I'll round it right there. Probably more sig figs than I probably included for any of the numbers in the problem, but c'est la vie. Cool. And there's your final velocity of this electron. Okay. Question number 2. We've got a uniform electric field that points in the positive y direction of 250 newtons per coulomb. We got a 2 microcoulomb charge that starts out at the origin and ends up at a point 50 centimeters in the x direction and 10 centimeters in the negative y direction. And the question is, what is this charge's change in potential and change in potential energy? So in this case, if you recall, change in potential energy is Q delta V. So, but we want to get this change in potential here, and we're relating it to an electric field and moving a certain distance. And that's where this equation comes into play. So it relates the change in potential to your electric field strength and the distance you move in that uniform electric field. So in this case, this is an example that is independent of pathway. So notice if I got this marker here, if I move it back and forth this way, is its potential energy changing? No, I'm not changing the height. It works the same way with a charge. If I move a charge back and forth along what's called an equipotential line or an equipotential surface where the potential is not changing, just like the height's not changing, it doesn't change its potential energy. And so in this case, if I take this lovely charge and I move it back and forth in this direction, so, well, the electric field's in this direction, and your potential is going to be changing relative to this direction. So notice, why might I have an electric field? What could be a cause of an electric field pointing in the positive y direction? What could be causing that?
A negative charge?
A negative charge where? Yeah, in fact, to be a uniform electric field like this,
Or negative charge?
negative charge at the top and potentially
Charge.
either one of these or both could be the cause here. And so if I look here, is moving sideways going to change potential energy at all? No. And so in this case, the 50 centimeter part going from 0 to 50, I couldn't care less. Doesn't matter. It's going down 10 centimeters here in the negative y direction. That's what's going to matter. That's the only part that matters. All right, so in this case, to get this delta V here, we know our E, 250 newtons per coulomb. And what distance do we move?
0.1 meters.
Cool. If we look at this for just a second, so should I be envisioning this? So is this charge positive or negative, first of all? Positive. So is it going to be gaining or losing potential energy here?
Gaining.
So notice, does it want to go this way? No. So when it goes the way it wants to go, that's when it lowers its potential energy. So if I'm doing the opposite, it's gaining potential energy here. So delta V here has to come out, in this case, positive, because for positive charges, they gain potential energy when they gain potential. So the potential is going up for this guy. And what do we get for delta V here? Cool. 25 what? Newton meters per coulomb, which is a volt. Awesome. So, and in this case, that's going to affect our change in potential energy. Q delta V, and our Q is 2 times 10 to the negative 6 coulombs times our 25 volt change in potential. And what do we get for a change in potential energy?
About 5 times 10 to the negative 5th.
Cool. And what's the units on that?
Joules.
Good. Where'd you get the joules from?
I just potential energy is measured in joules.
Good. A volt is a joule per coulomb. So if you have joules per coulomb times coulombs, the coulombs cancel and you get joules. You guys remember this diagram? Look familiar from earlier tonight? Remember what we solved for earlier tonight? We solved for the force he felt. And because we were solving for a force he felt, it was vector addition. So this question is a little different. Now I want to know at this empty corner right here, what is the value of the potential? Well, why is there any potential potentially at that corner?
Because there's 3 charges.
3 charges in the area.
Variance and potential.
Exactly. And so in this case, though, when I go to figure out how each of these charges contributes to its potential, how am I going to add them? As scalars rather than vectors, which is such a good thing. No breaking into components, no Pythagorean theorem, none of that stuff. So in this case, 3 charges, I'm going to have 3 components to adding up my potential. So if you call potential is K, Q over R, we're just going to simply add these up together. Keep in mind your Q here factors in if it's plus or minus. Make sure you include that. So in this case, let's start with the 4 nanocoulomb charge. What's the potential at this point due to that 4 nanocoulomb charge?
8.99 times, or K times 4 times 10 to the negative 6.
Nano.
Oh, negative 9, sorry.
Good.
Divided by 0.001.
Good. What about due now to the, let's go to the negative 1 nanocoulomb charge. K times what?
Negative 2 times 10 to the negative 9.
Oh, going to this guy next. Sorry.
Negative 1 times 10 to the negative 9 coulombs.
All over.
0.001 meters.
Since those are both 0.01 meters away, I thought I'd deal with those first. And then finally, K times his charge, negative 2 times 10 to the negative 9 coulombs. All over what? Square root of 2.
0.002.
Square root of 2 times 10 to the minus 3. So, or you could look at it one way. Let's just say that square root of 2 is 1.414. So it'd be 0.001414 meters. And do it that way. Okay. So, somebody just add these together for me. These are both negative. He's positive. What are we going to get here?
Why is the negative 2 nanocoulombs have a different radius?
So,
Oh, because you're going from
this distance right here. So it's the hypotenuse of this right triangle.
Almost there.
No worries. My calculator's just too far away. I'll let you plug and chug this one.
Okay, I got 1.425 times 10 to the 4th volts.
Anybody else get something around there? Does it make sense that it should be more positive than negative? Because there's 2 negative terms here and only 1 positive term.
The positive term is the biggest charge.
It is the biggest charge. And in this case, it's 4 times bigger than this. So in fact, in order to cancel out the effect of this guy, I would need to have a total of 4 nanocoulomb charge, or at least total of 4 nanocoulomb charge, exactly the same distance away. And this charge is helping. It's negative 1 nanocoulombs, the same distance, 1 millimeter away. And here's 2 more, but not 3 more. And it's further away, not closer. So definitely there's more positive than negative here. This makes sense. While I'm thinking about it here, you guys remember this problem we did earlier? We wanted to find where the electric field was 0. Did anyone remember where the electric field turned out to be 0?
5 millimeters to the right.
Yeah. 5 millimeters to the left. And we could have figured out that he's got 3 times a bigger charge, so 9 times bigger charge, so he had to be 3 times further away. What if I asked you, where's the potential going to be 0? Where's the potential going to be 0? well, where could the potential possibly be 0? So in this case, notice it's not KQ over R squared, it's KQ over R. So if I pick a point in the middle again, somewhere in there. So due to him, what kind of potential are we going to have? Positive. Due to him, what kind of potential are we going to have? Negative. Oh, who's got the bigger charge? Positive. By what factor? How many times bigger? 9 times bigger, which means who does it need to be closer to if they're going to equal? Ooh, how many times closer? Oh, so what would it be? Yeah, 1 millimeter here, 9 millimeters here. Great. So easier to do if it's not, don't have to worry about the square of the distance and stuff like that, but just wanted to show you the difference between potentials versus electric fields like we dealt with earlier while I was thinking about it.